Welcome, everybody. My name is Claudia Felser, and it's my great honor to introduce Anke Weidenkaff to you. She's the plenary speaker of this afternoon, and she studied chemistry in Hamburg, Germany, and got her PhD at the ETH in Zurich. So she did her habilitation in Augsburg and joined the Swiss Federal Laboratories for Material Science and Technology for a Sustainable Future at Empa, already at a time when we were not thinking about sustainability. At the same time, she was Professorin for Material Science at the University of Bern. Then she became chair for material synthesis and head of the Institute of Material Science at the University of Stuttgart, was visiting professor at the NASA Glenn Research Center in the United States and at the CNRS in Caen. Since 2018, she's a professor for material science and at the TU Darmstadt, and she's a director of a Fraunhofer Institute, a new Fraunhofer Institute research institution for materials recycling and resources strategies in Hanau and Alzenau with more than 100 employees. She served at many boards of the IMRC, at the board of directors. She's a member of the IMRC Bulletin and board member of the German Federal Laboratories for Material Science and Technology. She's scientific advisor for the German government for global changes, and she will join the UNO conference COP this year, representing Germany at this important issue. She is vice president of the German Chemical Society for Material Science, and she was president of the European Thermoelectric Society, and she got also numerous awards and presented one was, for example, in 2011, the Kavli Foundation Lectureship Award at the IMRC. So Anke had already a vision about a world without waste when we were still not thinking about this, and today she will use the e-mobility as an example to show maybe how the first steps can be done in this direction. So welcome, Anke Weidenkaff.
Thank you. So thank you very much, Claudia, and thank you very much for the invitation to speak here in this nice city, on this nice location. So can we please see my slides? Yes. So the topic of today will be efficient recycling methods for e-mobility components and materials, and I'm going to switch my slide. And the reason why I chose this topic today is the way to climate neutrality. As Claudia already mentioned, I'm, as a scientist, being member of this commission, which has to report to politicians about scientific advancement, and therefore I also have the chance to take place at the next conference in Glasgow, where we will make the mandatory long-term strategies as a major topic there. So you see that we are publishing other papers than we are used to publish, and so we call these policy papers. And I think this is very important that you all engage in policy making, because we have to be the authority for the scientific background for these very important decisions. And one of these decisions we already made is the defossilization of the mobility and energy sector, and we want to use only renewable energy sources for the electrification of the mobility. So we do not want to burn any fossil fuels anymore in the future. And this technology transition is always also a materials transition, and this means also resources transition, and therefore we have to work on enabling a circular economy so that we can enable this transition. And this is the outline of my talk today. I will start about criticality and criticality of elements. Then I will show you some examples for this e-mobility sector, and I will talk shortly about green hydrogen production with green materials, and then about a new way of manufacturing materials by using scrap for additive manufacturing. So as scientists, you all know that normally new technologies always follow the discovery of new materials, and that's why we are here together today to talk about those. And this is well known also in history, therefore we are even calling the ages according to the materials discovery. So we are talking about the Stone Age, the Bronze, Iron or Silicon Age, which we are now leaving for quantum computing, and we don't know what kind of age we are starting right now. But what is clear is that even 100 years ago, the people were developing energy converter systems according to the materials they discovered. So it always comes the material first and then the technology. So hundreds of years ago, the people only had stones and iron to produce windmills. And later on, they discovered other metals like steel, and then they could build a steam engine. And then later on, even more technical metals could be extracted from the ores and the minerals to produce combustion engines. And then afterwards, we had more and more elements available, like, for example, rare earth elements to produce semiconductors for solar energy converter or highly performing magnets for generators. And so you see it becomes broader and broader, the possibility of producing new materials, and then more and more technologies follow. And now we are having a new step ahead of us, and this is a defossilization, and we don't know what kind of materials we will use for such a step. But we already know that we're getting also into new problems, because this variety of technologies we are using also need a lot of new materials, and the availability of some of these metals is scarce already. So we call this critical. Even if some of these elements are not really scarce, they can become critical because they are mined under severe conditions, for example. And one example are the rare earth elements. And you know that there was a crisis in China, and they decided 10 years ago to stop delivering those, and we had suddenly no possibilities to produce technological equipment anymore. And you know, now due to COVID crisis, we have also a problem on delivering semiconductor systems. So this will become more and more aware that we need to ensure this delivery of these scarce or critical metals. So the rare earths are already nowadays considered critical. So we need those for highly efficient wind conversion facilities, so for the generators, or as well for the traction motors for e-mobility. And then there are other elements which are necessary, for example, for ICT applications, like germanium and so on, and scandium, and also they become scarce, and so these applications depend on those elements. And then there are other which are in the moment moderately scarce or critical, like the PGM metals, so the noble metals, or strontium or cobalt. They are needed for the e-mobility sector. And so this is the forecast of the next years, because we will all switch to e-mobility. So there will not be any fossil fuel burning system around anymore. So all the cars you see nowadays will be exchanged by electrical vehicles. And so we can already predict now that we will run out of lithium, dysprosium, cobalt, neodymium, graphite, or nickel. So all these elements will become very critical. So we have to find ways to make sure that we have them to produce the new technologies. So, and we can also see it from the other point of view. So here, once more, you see the supply risk of these raw materials for key technologies. But you can see this, read this in another way. You can read out here what will be in your waste bin in the near future. So you know that if you have drones or e-motors or fuel cells in in your use that they will end up very fast in your waste bin, because all these technologies have a very short lifetime. So even that the digitalization is giving us so much, for example, the possibility to make this conference here, and you can see it all over the world, is one possibility, but there are also disadvantages. All our laptops, they have a very short lifetime because innovation is so fast. We need to buy them every year, and everything is digitalized nowadays, as you know. So we already did a small step. We went from a linear society, a linear economy where we were just taking something, using it and throwing it away, to a recycling economy. So nowadays we are still exploiting nature completely to get our raw materials, and then we are designing, producing our materials and devices. Then we use them, and we are starting to collect them, and part of it, so 20%, is recycled, refurbished, and brought into a second life, but we are still depositing too much in air, in water, or in soil. And you know that we have this nasty little persistent molecule CO2, which is giving us this climate crisis. It's very hard to sample it again. So yesterday we had this talk about the artificial leaf. This is of course the holy grail, but in the moment it is very energy intense to get it back. So we should not dissipate our resources in the environment. And for this we are developing recycling strategies also in my institute. So for example, this is a very simple recycling of normal batteries. You just use a high temperature furnace for a pyrometallurgical process, and then you are recovering some of the valuable metals, so only cobalt or so is recovered, but the rest ends up in a slag, and this slag can only be downcycled or deposited. So this is not a way to start a circular economy. And then we are also working on technologies where we are giving, for example, car batteries a second life as intermediate storage systems for electricity, but also these second life will end up in an end-of-life product, and this has to be solved, this problem. So all these already available recycling systems unfortunately lead not to a circular economy. So to my opinion, we have to directly find methods to produce our products, our materials out of waste, so that we have a zero waste future and zero supply risk. And to my opinion, the possibility to recycle something is set in the very first minute of a material's design. So we already have to think about that when we are designing a material. And if this is possible, then we might come to a real circular economy where we can regenerate our materials. So if we want to come there, we have to define the criteria of criticality every day in use. So this concerns the social relevance, the ecological relevance, economic and technical relevance, of course. And so therefore we were defining a new figure of merit for the materials design. So nowadays, or until now, we all design new materials according to their performance. So we want to have high performing materials, but in the future we have to also think about the sustainability, so that you have these two factors as equal measure of a materials or successful materials design. So the old criteria you can find here. Of course, we want to have still efficient material, durability should be high, and programmability would be really nice. And but at the same time, and this is as important, we need to obey these ecological criteria, and economic criteria are also very important, as well as the criticality has to be taken into account, and the multifunctionality for the recycling of material, because it makes no sense if we are thinking about a recycling for technologies which are necessary today, because tomorrow we will have completely different technologies since everything develops so fast. So how do we do this evaluation? This is done in a certain way. We call this life cycle modeling. So in the computer, you can feed in all these impact indicators concerning ecological aspects, economic criticality aspects, as I showed you before. And then you are assembling all these data on the materials, the energy, and the information, and then you can generate a virtual process. And this is described by the input flows, the output flows, and the process parameters. And then you can design them on a computer, and you can find also alternative process change. And in the end, these assessment results go into your system from the beginning, and you have this feedback loop and can produce the more sustainable materials in the end. And here we have a little demonstration project which we found, and this was the development of an electrode material for electrolyzer system, and this is based on cobalt oxide, and the cobalt oxide has to be produced in nanoparticle form, so different templated methods were used. So these are the three ways of producing something, and for this production process we could assess a very important data set on the net process time, the global warming potential, so the CO2 footprint, the current density, so the efficiency of the material, and geopolitical risks. And we did this for all of these synthesis pathways, and all these data for all the steps of the synthesis of these materials go into this model, and then in the end you can pick out which process step could be substituted to have a more sustainable material in the end. So, and then the vision for a better recycling or circular economy is that we are digitalizing our resources so that we know what we have. Because nowadays, if we have an end-of-life product, for example, here a mobile phone, then we do not know the content of it anymore. So not even the producers, because the chain of raw materials for the production is so complicated nowadays and so global that we do not know what is the content of material in every product we are using. So therefore we are throwing it into the waste bin, and then a lot of hardware follows. So you need a lot of logistics to bring it somewhere to analyze it and sort it, this waste, this electronic waste, for example. And then we are bringing in a lot of energy to distribute the waste, and eventually, after all these hardware processes, we can recycle a part of it. And it is still in the 20% range, and some of this goes into retail and into new products. In our vision, we want to start in the first minute of a materials design and the production of a material to have the data set to make a product passport. So in this product passport, you have in a blockchain way, a very secure way to give the information what is in your end-of-life product. And so then you also need an intelligent waste bin that in the moment you're throwing away your end-of-life product, the information will be sent to a green materials production facility, because we already have the information from the synthesis, as I showed you in the slide before. We have already this data set. So this green materials production can be realized because we have the information of the waste content. So, as I said already, this digitalization is wonderful, and we are all very happy that we have all these little gadgets, but they also produce a lot of electronic waste. And the situation nowadays is the following. So we are producing more than 50 megatons of electronic waste per year. And only a part of it, so 70%, so 9 megatons, are going properly into a recycling process, because they also have a lot of value. So they are making, so some companies are making new raw materials out of them, and they can sell those. But most of the electronic waste is just not documented. And this is more than 80%, and this electronic waste, and this is a sad thing, contain a lot of persistent toxic content. So for example, this flame retardant, or even worse, these fluorinated hydrocarbons or mercury. And so it's a pity also from an economic point of view, because all this waste has a lot of value. And because of this value, we find our electronic waste in Africa. I don't know if you saw this movie. I can recommend this. It's Welcome to Sodom. It's about such a burning e-waste deposit of us, and the people living on this dump and taking out some of the valuables, and we really don't want to have this in the future anymore. So there is a lot of change also in materials design and materials development, as we see on this conference. So we have a big step for this Industry 4.0. So the fabrics of the future, they will look completely different than the fabrics of today. They will look like a clean room, because we will 3D print everything in the future. Not only the mechanical parts, but also houses and so on. So the material supply has, they already know that, so this is stolen from a material supplier. They are already producing the materials for the 3D printing fabrics of the future. And we have to make sure that these fully automated 3D printing materials are really sustainable and recyclable. And to show you how we could do this, I picked out this topic on e-mobility. So we all drive, or most of you, I don't know, Claudia and Stuart not, so they are driving already an electric vehicle, but most of us are still driving around with combustion engines. And we already know, no matter which scenario, looking at even big oil is predicting this, that we will have 100 million of electric vehicles in the near future. And here you see one of the vehicles of my institute. This is running with a hydrogen fuel cell, and in the future we will only see these cars. This is already decided. And what we need for such cars, I will show you in this talk here. So it's not only that you need new gasoline stations, because they will not be gasoline stations anymore. They will be hydrogen fueling stations like in our campus here, and or fast chargers. So the key components of an electric vehicle, like the one I was showing you on the slide, are the fuel cell, so the energy storage system or battery, then the electronic motor, and these ones with a permanent magnet, and power electronics, of course. And if we want to recycle these components, we have to first dismantle them, and these new recycling processes are necessary to recover the secondary raw materials. To do this, we started a center for disassembly and recycling of e-mobility components in Hanau, and this is financed by the Hessian Ministry of Science and Arts. And this is working in the following way. We have these electric vehicle battery systems. They look like this in a blow-up. And it's interesting that we have already more than 7,000 tons of those batteries now in our waste bin. Even that we are not driving around with these cars, because there's a lot of overproduction, and I was also astonished that we already have so much waste material before we even have done this transition to an e-mobility. So we have to be very fast to develop the recycling processes for those. So what we are doing is we are disassembling them. First you have to discharge them. It's also very difficult, because it is it's very dangerous to recycle those. You cannot just throw them somewhere, because they can explode and so on, you know all this. And then we are disassembling them in an automated way into the components, and then from these components we are generating the secondary raw materials, or recyclates in German, we call them Rezyklate, and then we are analyzing those, and eventually we can use them to produce new batteries. They will not be the same, of course, because the ones you find in your waste bins are not the ones you need nowadays. So, what is such a lithium-ion battery made of in the moment? These are more or less the components. We have the pack and module, which is a steel case and some plastic parts and aluminum, of course, for the casing. We have the anode material, which is mainly carbon, the cathode material, which is composed of cobalt oxide in the moment, but we are switching the composition continuously to more cobalt-free cathode materials. We have the separators, like Teflon, for example, and we have, of course, the solvent, which is also changing continuously. So in the moment, we know a little bit what is in our electric vehicle batteries, which we are getting, but we don't know what the industry will use in the future. And as I said, the recycling rate is really, really low, because we are only recycling 5%, because we only recycle the valuable metals in the moment. Lithium, for example, is not very scarce. You know, you find it in seawater everywhere, but in the moment it is mined very near from Mexico, in Bolivia, for example. And they have a lot of resources of lithium there. It's really wonderful for the country, but they also need a lot of fresh water to mine it, and this can cause many environmental problems for the region. So we should consider also to mine the lithium where we have it, so because lithium is very abundant, we find it even in Germany. You find it in your kitchen, in your cooking plate, contains also of lithium silicates. It is a little bit more difficult to extract the lithium in these urban mining processes, because you have to employ some mechanochemical, more complex, more energy intense process, but it is possible. So everyone talks about cobalt, because we all saw these horrible pictures of children mining, working in mines in some regions of Africa, and so some of the automotive industry partners of us decided already that they will never use this cobalt again. So for example, Volkswagen signed this, but they don't say when they will start to be taking rid of this cobalt from Africa. So nevertheless, as summary, we all know these problems and we have to do something about it. And as I said, we are setting up recycling processes for such electric vehicles. And this process is a hydromechanical recycling process. So first step is we have to open these cases with a water cutter. And so then you open those, and then you have an electrohydraulic process to decompose these cases and the components. And then we have a sensor-based sorting, a self-learning sensor-based sorting line, which I will present you in a minute. And then we have some hydrometallurgical processes, of course, for the wastewater treatment. Now my computer is stuck, okay. Okay. So, and this is in contrast, is an alternative route to the nowadays used pyrometallurgical pathway, which leads to a lot of slag. So this hydromechanical pathway will lead to fractionated, to fractions, and you do not have to go back to the pure metal. So you're saving time and energy and space for not all the time diluting and purifying the metals again. Because if you're going back to the cobalt metal, you are having additional steps for the purification which are not necessary, because in the end, for the battery, for the electrode material, you use cobalt oxide again. Okay, so here it is in a nutshell, our recycling process. we are starting with the automated disassembly, and then we have this electrohydraulic fragmentation method, the physical separation methods, then you can separate the plastics from the metal and non-metal solids, and then you can purify and pre-treat them, and then for some, so we collect the active material to make new batteries out of it, and then of course we have to treat the wastewater, and because the wastewater contains also very valuable resources. So the idea here is a functional recycling. We try to reuse the components in the already non-purified and non-metallic form. So, so to recover the strategically most significant battery components. Okay. Yeah, so then I told you that we are using a lot of water for this recycling process, and the water contains still a lot of important resources. So therefore we have to develop also new membrane and electrochemical methods for the recovery of these resources in the wastewater. And the industrial wastewater is, the amount of industrial wastewater is increasing, and you know also here in South America this fresh water supply will become a problem also with climate change. So we have to already make sure that we have the right technologies to purify our water. And also if we want to produce green hydrogen, I will come to this point in a minute, we need also pure water for the water splitting reaction. Cannot be done with seawater directly. So battery is fading. Okay. So another component of an electric vehicle is, of course, the electric motor. And the electric motor contains of a permanent magnet. And the permanent magnet material, the Neodymium Iron-Borne material, can be found in our electronic scrap, in our electronic waste. So here you see a typical picture of electronic waste. We have a lot of electric motors already in our combustion engine fueled cars, and also in other ICT equipment. So without magnet, nothing is running here. So, and unfortunately, they are very diverse, these products. So the recycling rate of neodymium is less than 1% until now. And the rest is really dissipated evenly and is landing in these waste bins like in Africa, like the picture I showed you. So why are we so dependent on these neodymium iron-borne magnets? The reason is the performance of these magnets. So they were discovered in the 80s, and until then we had other magnets, but since then we are really based on these permanent magnets, and there are until now, unfortunately, not so many substitution materials available. So we still need this neodymium for producing permanent magnets. And if you look at the market share value in terms of value in 2016, you see we have nearly 70% of all magnets are neodymium-based magnets, while the mass is still dominated by ferrites. So the rare earth elements are not so rare, as I said, but the problem is not the scarcity of the element, the problem is the mining, because they are mined under very severe conditions. If you're mining rare earth elements, then you also set radioactive dust free. And this is not very healthy, and is only done in parts of China, and we really don't want to do this. Because it is harming the environment a lot. So as you can see here on this picture, and we should find another way to mine these rare earth elements, which are so important and so wonderful for our application. So here you see the sum formula of such a neodymium-based permanent magnet. It's neodymium-2, iron-14 boron. So we have 38% neodymium in such a magnet, and a lot of other elements also necessary to make a really good permanent magnet. And we can also forecast that we will need more than 40% more of these neodymium iron-borne magnets in the near future. So therefore, we have to find a way to meet these demands. And we also have to find a way how to meet these demands in a sustainable way. So we need this not only for electric, for drivetrains, but also for wind turbines, of course. We need large amount of magnetic materials or consumer electronics for air conditioning and so on. So where do we find those magnets? Of course, in generators or in NMR machines and in electric motors. And here on this photograph, you see such a component of an electric motor. We find in a normal car, like in a Tesla, around 2.5 kilogram of these material. And to recover it, we have to either dismantle the motor completely, and this is hard because it is magnetic. You have to demagnetize it beforehand. And it is also glued and clamped, and it's a very tedious procedure. So therefore, until now, no one is doing this really. We developed a method where we can directly embrittle the material inside the motor with hydrogen so that we can recover it in a more sustainable and more energy safe way. So here, once again, you see the other applications of the permanent magnets, which are also important, but I will not go into detail. What is interesting is that even the best physicists don't know really what is making a permanent magnet. So it is very complex. Of course, it's a composition and the crystal structure and also the microstructure. We know that there have to be some impurities, so a really nice single crystal is not a good permanent magnet. So unfortunately, my movie is not running. Okay. Oh, good. Okay, but you need a very good knowledge on the structure-property relationship to produce large, good permanent magnets, and therefore you need a very good analytic, and we are using 3D atom probe tomography to find out about this grain boundary composition. So if you are producing recycling magnet, then the very important magnetic characterization method is these demagnetization curves, which have to be read in a careful way. So you have the coercivity and the remanence, and you need to have a certain fingerprint of these material. And for every application, it is a different magnetic field needed. So every electronic motor, every generator has its own requirements. So these magnetic properties, as I said, they depend not only on the chemical composition of the scrap magnets, but also on the microstructure of the recycled magnets. And you also have a certain particle size, and there's a whole to-do list, which you have to know when you're producing new magnets. Also, the oxygen content should be there, but not too high, and the carbon content should be moderate. So it is a kind of very complex composition, complex procedure to produce them. And then you have also the way of tuning the magnetic properties according to the application of these recycling magnets. So you have to govern these grain boundary diffusion processes during the production, and you have to have a good modification of the grain boundary phase by this addition of rare earth hydrides. So these combination and these grain boundary diffusion processes bring us the good properties of the permanent magnets. And somehow we lost this knowledge a little bit because all the permanent magnets are produced in China in the moment. So we have to also learn how to do this in a proper way, at least in Germany again. So here you see some more detailed, and I hope this time my video is running. So you have to analyze these grain boundaries in a very detailed way. So here you see some fingerprint of these recycling methods by atom probe tomography. you see the neodymium content, and at the grain boundary, the copper, the gallium, and the dysprosium. And so we need to make sure that the dysprosium is diffusing symmetrically into the grain, and also that we have this formation of the neodymium copper alloy at the grain boundary phase, and the agglomeration of the gallium has to also be controlled. And this white band gap, this white grain boundary phase is controlled by the hydride addition. So here you see the results of such an atom probe tomography of such a grain boundary. So this is as sintered. You see the copper content in this small piece, and the result of the analysis. And then after annealing, you see the neodymium content at the grain boundary, the copper content, and then important also afterwards it comes the gallium distribution at this grain boundary. And the correlation of this grain boundary diffusion and the properties has to be understood in a proper way. So, and then we want to produce large scale of recycling magnets, and this is done by melting the alloy, and the melt will be dropped on a water-cooled copper wheel, as you can see here, and this produces a certain microstructure, and we are producing large amounts of those, as you can see here, of these flakes of recycling magnets. And this is the reason also why I'm working at the Fraunhofer Institute and not only at the university, because there you can set up such a lab factory for the production of recycling magnets, and we can produce up to 50 kilogram batches now of recycling magnets. And not only the sintered magnets, but also hot deformed magnets and polymer bonded magnets until now. So we will not survive without fuels, so because it is really difficult to run an airplane just with a battery or large ships or so we need also a new fuel, and the fuel which substitutes fossil fuels will be hydrogen, but the hydrogen has to be produced. I have 20 minutes still. Okay, sorry. I was taking my time. So, okay, but to get to this green hydrogen society, we need also green materials for green hydrogen production, yeah? And for this, we started a new center, and it's called also Leistungszentrum for Green Materials for Green Hydrogen. And here we are looking on all the components for a hydrogen circle. So on the one hand side, we have to produce the hydrogen from renewable energy. And for this, we need materials for electrolyzers, and so membranes and electrodes have to be developed in a way that they are recyclable and sustainable, as I explained before. And of course, we also need new photovoltaic systems which are more efficient than the ones we are using nowadays. And here we are also producing materials, and we heard yesterday about the direct solar water splitting, and also there we need new, more sustainable materials. And then for the hydrogen storage and transport, we are working on new hydrogen storage materials. And here we can learn from our knowledge on the hydrogen embrittlement. You saw that for the magnet production, we are also already using hydrides. And then for the immobility, the components I showed you, here we need new fuel cells, batteries from recycling materials. So if we want to supply only Germany with green hydrogen as fuel for heating and for industry and for part of the e-mobility, then there are forecasts, very conservative forecasts, that we need at least 250 gigawatt green hydrogen produced in the near future. But how do we do this? Because this requires tons of platinum, iridium, and cobalt. So these materials will not be available. So we have to figure out how to recover them from waste material. So here you see one of the still biggest electrolyzer systems. It's in the Swiss mountains, and I was working with this already 20 years ago. And here we were developing a new membrane material because during those days, suddenly it was decided that we cannot use asbestos anymore, which was our favorite material for membranes. And we had to find very fast substitution materials. In the first minute you think, is this impossible to find it, but we found it. And so I think that we are able to substitute materials sometimes, and this is one of the proof. And also we have to also find the available material, for example, for the oxygen evolution electrode and also the hydrogen evolution electrode. So now the battery is gone, okay. And for this we need, so for an electrode and a membrane material, you always have a material which has to be recovered during the conversion process. And we call this a breathing mode. So for example, here we are producing carbon nanotubes from plastic waste, and we are mixing it with the black mass, so with the recovered oxides to produce an electrode which has to run in a bifunctional way. And yeah, then of course it would be really nice to have a direct water splitting reaction and not use a photovoltaic plant and an electrolyzer, to have this in one setup. And so here we are working on the development of new semiconductors for these photoanode. And also you need a second system, which is a photovoltaic system, because you always need an additional current for the counter electrode. So you need a good photovoltaic system as well. And here we are developing wonderful new photoabsorber materials, these hybrid perovskites. And these hybrid perovskites have to be also produced from waste material, because you don't want to release, for example, lead into the nature. So we have to recover it and produce new material out of this. So here, and unfortunately, Europe has already forbidden the use of lead, even that I think it's a wonderful element, but we should not use it, so we have to substitute lead in these hybrid perovskites, and therefore we are finding new compositions for these photovoltaic applications. And this is done in collaboration with other Fraunhofer institutes, for example, the Fraunhofer ISE. Here we are developing this, this new solar cell where we are adding the perovskite on top of a silicium solar cell, so it will be a tandem solar cell. And for this application, we need to find a good photoabsorber, which does not contain lead. And you see our nice old Fax crystals. They were wonderful and had a really nice property, but they all contain lead, so we had to go to the lab and find a new way of producing lead-free photoabsorbers for such a tandem cell. So the material screening is done in a way that you first ask the theoreticians to make some predictions, and then you go to the lab, and then you're trying to, here in this case, work in this cap system with the silver, the copper, or the sodium. And then in my lab, they are producing this beautiful large single crystals of all these materials. Why single crystals? Because you have to determine the band gap in a certain way. And also we want to have a synthesis process which is sustainable already from the beginning. So here, normally you're using hydrothermal methods to produce these single crystals, to grow the crystals. But we heard also this in the talk, that sometimes also the chemicals have to be recyclable. So we are tending to, on the one hand side, we are using microwaves for heating, and we are also using new mechanochemical systems to produce the material, and we have to recover the chemicals afterwards. So this is a tricky thing to really upscale the synthesis method. And then what you're doing when you're developing a new material, you look at the crystallographic data and you try to find rules for the systematic synthesis. Then you're looking on the structure property relation again, on the band gaps, and then you have you collect all this data and try to understand the theory and improve the theory for that. So since I'm running out of time, I will come to my very last topic. Sorry, I have a lot to talk today. So in the end, we have to find a way for these fabrics of the future to, because this clock is not working fine. It says I have 12 minutes, but I see you have to correct this one, huh? Very confusing because I thought I have a lot of time. So if we want to use our electronic scrap as feedstock, we have to find a way to first treat it right. So in a typical way, if you have this electronic waste, you shred it, and then you have a fraction which contains all kinds of materials in one fraction. So what we are doing is this electrohydraulic fragmentation, and this is done in a setup like this one. So here you are having your components, for example, batteries, you are having a spark discharge, and then you have this shock wave, which then decompose the material on their weak parts, and so you have this very selective separation of different materials. And here is, as an example, one e-waste recovery from scrap electronic waste, very old. So you are doing some pulses and you can recover parts of these materials. And then afterwards it has to be sorted, and this is done in this fully automated modular sorting line, which we set up in our institute. So here we have different processes. As I said in the beginning, it's a lot of hardware, a lot of sensors and separation methods. So you have these magnetic drums, eddy current separators, and also a lot of magnetic systems to separate the metals. And this is very flexible, this setup, and it is learning itself about the waste which is coming in, because we have a large database here, and the setup recognizes the waste which comes in. And then in the end, we have here such a result from a car battery recycling system. So you can separate the metals from the plastics and the active material. And with the active material, the electrode material, you can produce a new battery which should run like the old one. And then the future, of course, is the 3D printing, the additive manufacturing, as I said. And normally you will not produce a battery from a scrap battery or, I don't know, magnetic storage system from one in the waste bin. You have to be flexible. You have to look what is in there, and then innovation have to take place, and we might need completely different materials. But what we need is clearly a feedstock for the 3D printing. And the feedstock can be formed, for example, by this hydrogen embrittlement. Here you see, for example, such a scrap metal, can be an intermetallic, and then you powderize it by just bringing it into this hydrogen furnace. And this can be done also with a full motor. And then you have the powders, and you can either produce a recycling magnet. Here in this case, it was a Häusler material. Or you can use these powders to produce powders for the 3D printer. So this is a new setup we set up for powder production for these alloys. And then we can 3D print magnets, which is a really tricky thing. It's not so easy because you have to understand that if you're having the normal alloying with the induction melter, so you have the hydrogenation, you have the milling step, you have the dehydrogenation, and normally we are using these casting procedures, as I showed you in the other video. Now we have to do the laser powder bed diffusion, fusion experiment, so you're melting it with a laser and it has to be recrystallizing in a certain way so that you get this microstructure as I showed you beforehand. So there's still a way to go to have 3D printed magnets, but we are on the good way. So in the end, I think as a conclusion, I can tell you that in the future we will not deposit this waste material to pollute the environment, but we will find recycling strategies to use, for example, e-waste or e-mobility waste to produce feed powder out of it and find a more resource efficient manufacturing because you have less waste in additive manufacturing. And this will hopefully help to heal Mother Earth in the future. So this is our contribution on the better future, hopefully. And I have to acknowledge all my co-workers. Of course, Claudia is working a lot with me, and the funding organizations. Thank you.
I wonder if the holistic evaluation that you show us should be defined locally, or do you think that it has to be like a globally, something that we do everywhere, or locally we have to find out?
Very good question. So of course, since all the production of raw materials, we have a global society, so we will still import, and this is also good, these trading all over the world, so we will still be depending on resources from other countries. So we have to have also spatially a good holistic view. But you have to start somewhere, and we are planning to first look at a system like Germany also to see what's coming in and what's coming out before we can have a global model here. So. I don't know if this is answering your question.
Excellent.
It is tricky because,
Thank you very much.
Hi, Professor. Thank you for your conference. It was really eye-opening. I have a question in the part where you are speaking about the hydrogen. Why asbestos is not usable for membrane application for hydrogen generation?
So you're asking me why the membrane application, I couldn't.
Why the asbestos is not usable as the membrane?
Asbestos, we are not allowed to use asbestos anymore because it's forbidden. It is damaging your lungs. It gives you lung cancer. And so it was withdrawn from the market. Unfortunately, I don't know how it is here, if this is still allowed to be used, but we had to remove it from all our products. And now it is somehow deposited in some mines or in some caves. One day, I don't know, future generations will find a way how to treat it. I think it's a disaster. It is sometimes better to reuse it and recycle it directly to get it out of the way. But in the moment, it's just stored away in some mines. Yeah, we are not allowed to use it anymore for our membranes.
Oh, okay. Thank you for the answer.
This can happen sometimes. I don't know, the older people among you remember this maybe still. And also, I don't know, there were other, like this Fluorkohlenwasserstoffe. So these were persistent chemicals, and they were identified to harm our health, and we had to eliminate them from our industrial processes from one day to the other. And then in the beginning, always the industry said, no, it's impossible, we will never have a mattress anymore, and so on. But it is possible. So if material scientists like you find solutions, and industry is willing to try these new solutions, then we always find a way. I'm pretty positive about that. So, because if one gets older, one knows that also these lead-containing additives in gasoline and so on, they found always some substitutions and some other materials which are better for your health and the environment.
Thank you for the very enlightening presentation. My question is related with nanotechnology. Do you think nanomaterials could help in this running process?
Yeah, it's a very good point, because the nanomaterials, they have also, we have to make sure that they can be recycled. As you saw also in the other talk, they agglomerate, and sometimes you need them deagglomerated in the future, so you have to find also production ways to recover them. One very good example is we are still using combustion engines, and we need an exhaust gas catalyst, so the three-way catalyst. And the three-way catalyst contains noble metals like palladium and so on. And the palladium is in a nanocrystalline form on top of it. And we are distributing it in the environment because we always lose parts of these noble metals into the environment. And if something is in a nanoscopic form, it can become very harmful because it is a catalyst. You should not swallow, even if it's a noble metal, nanocrystalline palladium. So yes, nanomaterials are super important and very good for applications. So for example, we heard about nanotubes and nano iron oxides for hypothermia and so on. It's very important, but we also have to make sure that we design them for recycling so that they will not distribute finely in the environment so that we cannot recover them. But they are important, but we have to take this into account. Yes, and also the chemicals for nanoparticles.
There's a last question, I think, and then unfortunately we must close this, but there's a last question.
Thank you very much for your nice talk. I'm here.
Yeah, it's very hard to see something.
So, as you said, we are material scientists, and in our process, we are always thinking about to make less toxic process. What about your recycling process? I mean, recycling process itself is sustainable, because I saw those melting temperature and high temperature. Does it make some other emission to the atmosphere?
Yeah, it's a very good point. We have to also use the right chemicals to not produce more waste than we are treating. And the idea is also to bring for example, the solvents in cycles. So when we are talking about micelles, for example, so these microemulsions, you have to make sure when you're using them for recycling or for the production of nanomaterials that you are keeping them in the cycle. You should not discard them. So this is a trick, and I think this is something we have to learn in the future, that also in industrial processes, if we are upscaling a synthesis method, so the chemical industry has to learn this, not to emit anything anymore. And if we are developing recycling processes, of course, we have to treat our new industrial wastewater in a way that we can reuse it afterwards.
So if there is no urgent question, but Anke is here around, and she will be happy to give more advice to the material scientists to think at the beginning about the end of life of their materials. So thank you, Anke, very much. And this is, I close the session. Thank you. Stuart, you should have remembered me. So Anke gets also a certificate. I was sure I forget it. And what happened, I forgot it. Okay, so Anke, yes. Thank you very much.
Is it okay if I'm to say I'm catching feelings from all the dealings? Am I astray? What do you say? How are you feeling? Is it the same? I hope you're not planning to waste my time. To my surprise, that was her reply. Now we a vibe. It's been a while and such a ride, the stars align. I love the fact I didn't let her go. She loves the fact that I just let her know. Now we're together, it's a different mode. We getting crazy in a different role. I love the fact I didn't let her go. She loves the fact that I just let her know. Now we're together, it's a different mode. We getting crazy in a different role. We getting crazy in a different role. She loves the fact that I just let her know.